Hello, everyone. My name is José Moreira, and I'm here to talk to you about my work on depth modeling to assess climate change effects on temperate and subtropical fish species. Although my work is on depth modeling, it is part of a bigger project that studies different impacts of climate change on fish, including fish's biochemical composition, fecal and nitrogenous losses, respiration, and growth. My work on depth modeling focuses more on the effects on growth. Particularly, we are studying two aspects of climate change. Global warming, in this case the seawater warming, and ocean acidification. And thus we are studying two forcing variables, temperature and pH. Four species were chosen for this project, two temperate species, the white sea bream and the Senegal Stone, and two subtropical species, the zebra sea bream and the brown tank. The idea behind this choice was to choose species that were somewhat comparable. So the white and the zebra sea bream are from different climates, but they both belong to the same genus and are both pelagic fish. And the Senegalese sole and the brown tank, they are not that closely related, but they are both benthic fish. However, we are still waiting for data on the brown tank, so this presentation does not address this question. The methodology included the creation of a depth model that includes both temperature and pH level. I'll dive more into that later in this presentation. But for the use on the model, parameters were re-estimated with the DEB2021 method. I used the files on the DEB2021 collection, and I added more data from the project's own experimental data and also from some other sources. The experimental data of the project came from two contributors, the JMoreira laboratory and the Olhão Pisciculture pilot station. For the Senegalese Stone, new DEB2021 files have to be created since the species is absent from the DEB2021 collection. Although experimental data, only the data from the Kiel laboratory included the pH conditions, and so this data was the main focus to predict ocean acidification effects. This data includes 4 scenarios for each one of the species, and these being the 4 possible combinations of 2 different temperatures and 2 different pH levels, as the figure shows. For the zebra sea bream and the Senegalese salt, these temperatures are 19 and 23 degrees Celsius, and the 2 pH levels are 7.7 and 8.0. For the white sea bream, the values are slightly different, 19 and 24 degrees Celsius, and 7.4 and 8.0 on pH. Still about the same data, I present here some graphs on the differences between the 4 scenarios for each species. These represent the weight variation with time, and each point represents the mean value of the individuals measured on a specific day of the experiment. An important disclaimer here is that in some cases the points may not symbolize the true mean value, since sometimes not all the individuals were measured. And so the mean on such cases is the mean of a part of the population and not of the entire studied population. So only some randomly selected individuals rather than the entire studied population. This happens mostly on the white sea bream and on the Senegalese salt, and does not happen at all for the zebra sea bream. And therefore, the graph for the zebra sea bream is more representative of the true growth evolution than the other 2 graphs of the remaining species. And that also might be the reason why the graph for the zebra sea bream looks a lot more clearer here on the left. Focusing then on the zebra cyprian, we can clearly observe a higher growth rate for the higher temperature scenarios in red and yellow here. And regarding the pH, we cannot really see a notable difference between the brown and green line, but between the red and yellow line, we can see a slightly higher growth rate for the more acidic scenario. In the other graphs, it is hard to take conclusions because the slope varies a lot, and there's the measurement issue I just mentioned, so I think I'll just skip them for now. Now, about how I took temperature and pH into account on the parameter estimation. Temperature was accounted by the Arrhenius equation. It's pretty standard on that, so I don't think I need to dive more into that. And pH was accounted by making Pn, the volume-specific somatic maintenance rate, dependent of the stress factor through this equation actually, where S is assumed to be higher or equal to 0, and an S equal to 0 means no stress, and is assumed here to be our highest pH value on the previous data, so a pH of 8.0. So moving on to the results. On the parameter estimation for the zebra cyprian, we obtained the mean relative error of 0.17, and we obtained the stress factor of 0.02, meaning a 2% increase on the somatic maintenance rate for the lower pH condition. The stress seems to go against the graph of the data I've shown you before, here on the left again, where it appears that there is higher growth for the more acidic condition. But there's an important detail here, is that we have here the time values as days after the start of the experiment. That's the only time values we've got from our partner. And we do not have here the age values. And because of that, we calculated the age on the first point by back calculating through the von Bertalanffy equation, and then went from there with the other ones. And as you can see, the first yellow point here is lower than the red. So if the horizontal axis was age, we would see the yellow line being pushed slightly to the left and giving something like this. And suddenly the yellow and red lines seem to go more towards what was expected. Even though the axis here is still not the true age, but time since metamorphosis to be more precise. But it still gives us a good idea of the age difference. And at the right, I included graphs of the explanation with the fit on the year laboratory data. And now moving on to the next species, the Senegal Stone. We have a very similar mean relative error to the previous species, about 0.16. This time the stress factor is 1.12 times 10 to the minus 8 power, so it's very close to 0, meaning pH had practically no influence on growth. Now for the last species, the white cyprian, again we have a very similar mean relative error, but this time we obtained a much larger value for the stress factor. However, this higher value is very likely not to be due to a higher pH influence, we think, but due to an overfitting problem. Because by looking at how the curves fit differently, the cases with higher pH where there's no stress factor on the top, again, comparing with the cases with lower pH on the bottom, we can clearly see the fit is much better here on the bottom. And I included the relative errors here, so you could see better how the fit is much better on the bottom category. This is most likely due to the stress factor being an extra free parameter that is giving too much freedom for the estimation to fit the data vector here on the bottom cases, since the top cases don't have a stress factor because they are the condition we assumed the stress factor was 0. To overcome this, we decided to rerun the parameter estimation with the stress factor fixed at specific value to look for a more realistic value where we wouldn't see so much discrepancy between the top and the bottom, while still maintaining a similar mean relative error. Here I'm showing you one of those estimations where the stress factor was fixed at 0.1, meaning a 10% increase on the maintenance rate. We can see that the discrepancy decreased between the top and bottom graphs. However, there's still a bit of discrepancy. And in fact, this discrepancy is impossible to remove completely because even without a stress factor, or a stress factor of 0, there's discrepancy. That's because the estimation already naturally fits the data on the bottom graphs better than it. And because of this, it's basically impossible to choose a specific stress factor using this fixed stress factor method. I included here the results of a stress factor of 0.1, but I could have just easily have included 0.01 or 0.2, and the discrepancy always be there. Also, very importantly, we discovered that for the Senegal Stone, the species that I presented right before this one, when we removed the stress factor being higher or equal to 0 filter, we used a filter for that on our predict file. And when we removed it, there was an overfitting problem too. Stress factor became negative, which would mean a decrease on the maintenance rate instead of an increase. But the problem is that it only stabilized at a value lower than -1, meaning a negative maintenance rate. And that would not make any sense here. So, summarizing, we have very similar mean relative errors of around 0.17. And we have very different stress factors, very different conclusions. We have around 0.02 for the zebra, almost 0 for the Senegal Stone, assuming a stress factor higher or equal to 0, using that filter. And without the filter, there would be this overfitting problem. And for the white zebra, stress factor of about 0.81 with this overfitting problem. So with this, we can conclude that the temperature effect was well predicted by the regular Reynolds correction. And we can conclude that the acidification effects were varied. For the zebra seagreen, we obtained a small effect of pH on growth for a 0.3 decrease of pH. For the Senegal Stone, we obtained a negligible or possibly positive acidification effect on growth for a 0.2 decrease on pH. And by positive, I mean there will be actually a decrease on the maintenance rate instead of an increase, which would leave more energy for growth instead of less energy for growth. And then for the white seagreen, the effects were inconclusive due to this overfitting problem. So this means that there is still work to be done here, particularly on overcoming this overfitting problem on these last two species. So comments and suggestions are very well appreciated and encouraged. And that's it for now on my part. Thank you all for having me here, particularly to the organizing community. And I also want to thank all the people and institutions involved on this project and the Portuguese Foundation for Science and Technology for funding the project. So now feel free to give me any comments and post any questions. I'll gladly answer them. Thank you.